So what we're going to do today, week 2, class 2, is give you an introduction to what we call the Coriolis Theorem. We're going to use it a lot in the next few weeks. We're really going to use it extensively. And give you, and once we're done with today's work or lecture, you'll be able to do the practice problems and test practice problems as we go along in the classwork. You've seen this before, but you may not have seen it with BZ notation. So I consider it incomplete without this notation. I know you'll disagree on that probably, but no one has ever been able to show me non-ambiguous Coriolis theorem without using this notation. So there's nothing in here that's extra. All of it is needed to mathematically define what we're doing. So we take an arbitrary vector, I call it rho. Normally it's a position vector. Could be any vector. And we put it in two coordinate frames. And we're used to using the V frame and the B frame. So we know that the B and the V frame, they could be any two coordinate frames, but they related to each other via the Euler angles. So we know that. And therefore the B frame can rotate with respect to the V frame, psi dot, theta dot, phi dot. Yes. And we talked about that vector yesterday. We'll talk a little more about it today. So how would I express that vector, the rate of change of that vector, as seen by someone who's fixed in one of those coordinate frames? In other words, you're riding on this coordinate frame. So if you're in the B coordinate frame, this dB dt means the rate of change you see while you're sitting on those axes. Those axes are not allowed to rotate with respect to you. The same with the V frame. So if you have the rate of change of rho and you want to see what it looks like from the cockpit, if the B is the pilot, and you want to see what it looks like looking northeast down on the E frame or the B frame, then you need to use this formula. dB dt rho equals dV dt rho plus the angular velocity of the V frame with respect to the B frame crossed into rho. Now we don't use the cross product in this course. The cross product is a mathematical operator. I know you've seen it in dynamics. I wish they would just throw it away. It's actually a matrix operator. So rather than program up the cross product in MATLAB, what we do is we just use a matrix equivalent. So this capital omega, notice it carries the same subscripts. The capital omega is the cross product operation. Omega V cross is equivalent to capital omega V/B, the angular rotation. I'll show you what elements are in there later. The relationship is always fixed. So we're always going to use the cross product capital omega for the cross product. That allows you to easily program it in MATLAB or whatever programming routine you're using. So if we've done then the Coriolis theorem, looks like dV dt of rho equals dV dt rho plus cap omega times rho. And I wanted to emphasize that the B frame and the V frame and the rho vector are totally arbitrary. I can put any frame I want in there. Of course, if I change V, I have to change. If I put, for example, if I put little e in here, then I have to put little e wherever the V was. But any letter can go in there. The other thing I wanted you to notice is I have not yet put this vector equation. This is a general vector equation. I have not yet put it into a coordinate frame. There's no BZ comments. So this is uncoordinatized. So this is going to tax our memories for a little bit. We're going to have to remember that everything to the left of the comma is a vector equation, and everything to the right of the comma is going to be the coordinate frame that vector equation is expressed in, which we haven't done yet. But whatever goes to the right of the comma has to go to the right of the comma in every term. You can't be mixing up coordinate frames and multiplying vectors together. They all have to be projected onto the same coordinate frame once I put the comma in there. Okay? And what do we mean by projecting? We drop a perpendicular from that vector to another vector. Questions? The two solutions we have, the first solution A, find Cv2b dot, integrate it fast. What do I mean fast? 200 hertz, real fast, because there's no trig functions in it. Maybe you have a little card do that. Just have the integration rate really fast. Then every 1/45th of a second or 1/40th of a second, pull out psi theta phi, show them to the pilot. That's one way. But that's what we're going to do the rest of the day today. This 8. The other way is to use quaternions. Convert your Euler angles into a 1/4 vector, which we'll define tomorrow. We'll define what that is. Convert the quaternion into a 1/4 vector. Find the Q dot, integrate it 200 hertz, 300 hertz, every 45th of a second. Convert the Q vector back to the Cv2b matrix and pull out the elements. Show it to the pilot. Okay, so what are we after? We want to get Cv2b dot. That's what we're after, right? Because we don't have to divide by 0 if I get that. So we coordinatize it. I picked the coordinate. The coordinatization is arbitrary, but you'll get a different answer if you don't coordinatize it this particular way. That doesn't say it's wrong. It just be different. So I picked dB dt, put everything in the BZ B coordinate frame with pure derivative of Cv2b rho comma b. That allows me to use the chain rule on these two, and that chain rule spits out what I'm looking for, Cv2b dot. Spits it out right there. It leaves a pure derivative over here, but I said, oh, well, I know the pure derivative is the same as the derivative with respect to that V frame. So I put the V frame back in. Then I come back and look at the substitution over here at the end. Once I make that substitution, and hopefully you can see that we've got the orange and the orange are the same term, the red and the red are the same term, the blue and the blue, and the green and the green are all the same term. And I make my the last thing I want you to see is that this and this are the same vector. So if you make this last substitution, Cv2b dot falls out and you're done. Okay. So we applied the Coriolis theorem. Yes?
What is the QED stand for?
Proof complete. That's Latin for proof complete. Once we got Cv2b dot as a function of the rate sensors, look what we have. This is the rate sensors. That's PQR. So PQR is going to determine this matrix. And I'm just going to multiply the matrix by the old Cv2b as a matrix multiplication. There's no trig functions in there. You see that? No trig functions. 200 hertz. Guess what I get to use? Every 50th of a second, I want to show the pilot something. So it looks like it's smooth. So every 50th of a second, I'll go into this matrix and pull out psi theta phi using a trig function and show it to the pilot. But there's no divide by 0.